Previous video, I showed you how to approach the modeling of this problem 7 with these two tanks and 20 gallons per minute with a concentration of 2 pounds per gallons of salt going in the first tank and having it connected to a second tank, which is also holds 20 gallons per minute with 20 gallons per minute coming in and 20 gallons per minute coming out. We generated a model, and assuming our model is correct, then we were asked to find the complementary solution by hand. And hint, lambda 1 and lambda 2 are equal to -1. You may check Matlab. So here, we got the right answer, as is hinted here. But let's see if this solution works. So I'll show you in Matlab how to check this. So if you go over to Matlab, the first thing we're going to say is clear all old variables. And that is done with the command clear all. Then what we do is we're going to define the coefficient matrix. So that was the matrix. So to define a matrix, you open the square brackets, and that was the matrix -1, 0. Put a semicolon to indicate the end of that row, and 1, -1. Put a semicolon at the end of everything to not have it output over here, which clutters everything. So unless you want to check it, you can do that to not have it output. And then what I'm going to do, well, first of all, is I'm going to check whether the eigenvalues were correct. So checking for eigenvalues and vectors, and you can use the Jordan function, which outputs vectors and values. So you need to give it a matrix output so that each output is properly given to a specific entry. And then here we would put the Jordan and the matrix to which we want to apply the Jordan. Now I won't put a semicolon here because I want it to output here and check. And now once we check, what we want to do is we want to generate the complementary solution. And our complementary solution was, let's call it x sub c of t. It was equal to c1 times e to the, well, we'll do the vector first, times the vector 0 in the first row, 1 in the second row, times e to the -t. All of that is going to be added to another constant, c2, multiplied by another exponent, e to the -t. Because remember, I'm doing this, and I can factor out the e to the -t. And now that I factored that out, I'm still going to multiply everything by a first vector, which is the same as the one we have on the left, 0, 1, times t, plus a second vector, which is actually 1, 0. And now I realize that I have a bunch of variables that I need to declare. So I'll go ahead and do that with the sims command, and I'll put that I have a t, a c1, and a c2 that I want to treat as variables. That's going to generate my solution, and I want it to output just to check whether it's written properly. And then checking the solution, this is the most important part. What we do is we take the derivative of our solution with respect to time. Now the only, let's put the time here, just to be sure, with respect to time, and that has to be equal, and equality is given by two equal signs in Matlab. It has to be equal to a multiplied by our solution, x sub c. So if we do all of this by pressing Control Enters, we notice that we get an identity on the left and on the right. So we know that this is actually the right solution. And we have the same values for the vectors. Well, actually, we don't have the same values here. We have -1 and -1. These are the eigenvalue, and these are the eigenvector. I am not sure why it gives a 1 here. That's why I'd like to sometimes use the eigen function instead, because I feel like it's a little clearer. Here it outputted the 2 eigenvalues. So I'd say always use this one first and then check if you have a repeated root, then it might be better to just do it by hand to not get confused by this. But in either case, we did find what our complementary solution is, and it seems to be working because we have the same things on the left and on the right. And so this is how you check it. All right, I'll see you next part, which is going to be part C for the particular solution. See you there.